Physics 2211, Lab 1. So the purpose of this lab was to observe an object, in this case a soccer ball eraser, in constant velocity. Velocity is a vector quantity, so the magnitude and direction of the vector stays the same throughout the entire observed period. I observed this data in only one direction, the x direction, and then compared this to a computer model to see the difference between the predicted and observed data. I'll go into more detail with the coded model later, but the basis of the model was the kinematics equation. Using Newton's second law, F equals ma, I can derive the kinematics formula shown below. I used this equation because I measured position and velocity over a set time period, and because there was no change in the motion of the object, I know there was no net force according to Newton's first law, so I can simplify this equation to this. The system for this equation is the soccer ball eraser, and the surroundings are going to be the table, air, and anything that is not the eraser itself. For this experiment, since we want to observe constant velocity, we're going to ignore friction, air resistance, and any other force that could be acting upon the ball. Here are the derivations for exactly how I got those equations from Newton's second law. Working from the top down, I first suited velocity for times mass for momentum. By then factoring out mass and using v average, which is equal to the sum of the final and initial velocities over 2, as well as equal to the final position minus initial position over delta t, I found the final formula. Once again, because there is no net force, the entire F-net term of this equation will go to 0. Here's the video of our group conducting the experiment. Please note that I did not use the whole length of this video, as you can see the soccer ball eraser slowly slowing down towards the end. Because of this, only a small portion of the video was actually used, and by using the meter stick as a reference for dimensions and manually tracking the position of the ball, I came up with the data shown above. Here is the code for the computer model that was created. While the code shown here was given, some lines need to be edited. These are shown in the pictures to the right. My group weighed the mass of the soccer ball eraser, and I updated that line, calculated an average velocity from the tracker data, and also updated the velocity vector line, and then I updated the position vector by updating the initial position found from the tracker data. I tried to set the ball's initial position equal to the origin in tracker, but this wasn't perfect, so I added in the initial position I calculated from tracker to try to be as precise as possible when later comparing the data. I also updated a line of code that updates the position at each time step by a set amount. This set amount is equal to the velocity, which is constant, times delta t, which was set as 0.033 seconds, because that was the frame rate our camera captured the video at. Thus, the time steps for the tracker and code were the same. There was no net force applied, so I didn't worry about that line of code, which means I really didn't have to input the ball's mass, because this would only be necessary if a net force were applied. Here's the data which was received from the code. You can see the slope of position versus time is linear, meaning velocity is constant in this model. Here's the comparison between the two sets of data. When I compared the two sets, I can see the computer data overestimated the actual data. This is because the computer model is a perfect scenario, while in the actual trial I couldn't completely negate the forces of friction and air resistance. Thus you can see that over time, the actual object slows down, while the computer model does not. Alright, if the axes were flipped, both slopes of the graph would be negative, because the object would be moving in the negative x direction instead of the positive x direction. As mentioned earlier, in the coded model there were no other forces. However, in reality, there were friction and air resistance forces, which, because it was real life, did have an effect on the object's motion and could not be summed to 0. Some ways I could have potentially improved this experiment were by pushing the ball with a greater force, so that when I captured a period of time when it seemed to be moving at constant speed, friction and air resistance would have had a lesser effect. I could have also calculated our v-average with more data points, so that the v-average would be closer to the overall average instead of the initial velocity, as I calculated this mainly with data points from the beginning of the experiment. The table was also rough, and our ball was not perfectly spherical, which also could have contributed to the uneven motion. However, If you take into account that friction and other forces were not entirely neglected, our model still serves as an accurate representation of the laws of motion. Thanks for listening!